Well, as this new hypothesis requires some demonstrations, and before presenting the original and fundamental idea that reveals the hidden morphologies of atomic nuclei,
we will expose the mathematical tools that will serve us.
These tools are 4 in number. First is the chaotic. Secondly, fractals. Third, foam structures. And fourth, quasicrystals. But do not be frightened by these new mathematics.
In fact, we will only use very simple rules, without going into long complex documents and obscure comments.
Therefore, let's take some interesting information into the science of chaotic. It is recalled that the chaotic, or nonlinear mathematic, appeared with the study of the movements of meteorology. The purpose of these studies relies on the ability to predict future climate. But we remember that Jeff Goldblum has taught us that the world of chaotic is unpredictable. And the movie industry has also informed us about the butterfly effect, phenomenon describing an event as small as a butterfly moving in Asia or Africa could trigger storms in America. In fact, this notion is derived from mathematical formulas Edward Lorenz, who was trying to describe an atmospheric model. And this model developed a curious feature called strange attractor. Indeed, we observe that the trajectories tend to regroup and build under a well-defined shape, the strange attractor. But for us, this concept is very important and very useful to investigate the fundamental particles. Of course, we remain in the negative area of non-predictable. But we know now that under certain macroparametric conditions, it appears strange attractors specific and clearly identifiable. And if it is impossible to know their numbers and their positions in space, on the other hand, we know that, on formally discerned situations, we will encounter significant strange attractors. With these rules of chaotic, we can use our knowledge of the early stages of the Big Bang original. So after the first inflation, came the dispersive explosion period. And the strange attractor typical of this period is the winding spiral, classical form that is found in the turbulent phases, where the material is wrapped in multiple scrolls. One can also observe these forms of turbulence in the scale of the universe, and with the galaxies and winding spirals. But the chaotic also informs us that these spirals wrap around a circular central limit, at variation speeds depending on the viscosity of the medium. Therefore, with these chaotic data, we can say that with almost zero viscosity, the spiral will put an almost infinite time to reach its limit circle, as is the case in the vacuum of the universe. But we know, since the discovery of the background noise of the universe, that a fossil light ray at 2.7 degree Kelvin bathes the entire world. Radiation which is the trace of the original Big Bang. And using the rules of the chaotic science, the first idea is to combine the circle limit to the fossil ray at 2.7 degree Kelvin. And consequently, to consider any radiation in the form of a limit circle moving in a plane. This explains, in particular, the phenomenon of polarization of the light, where only planes aligned to the filter can pass through the grid. The second idea is to be interested in the new hypothesis of the string theory. Indeed, this theory states that at the quantum level, there would be very little energy structures, called many strings, which compose the interior of the so-called fundamental particles. And at this time of the presentation, we can sketch the morphology of the photon as a turning limit circle in a plane. Now we will still extract another rule of chaotic. If the typical strange attractor of the dispersive phase is the spiral and the circle limit, on the other hand, just before the dispersive phase, the strange attractor is the torus. Many strings then turning on the walls of the closed tube. Thus these torus appeared at the end of the inflationary era, just before the start of the dispersive era. And it is during this short transition period of the universe that billions of torus were formed, then disintegrate into limit circles to form the fossil radiation. All torus. But in fact no, because some of them survived. And we'll see how. Now let us present a second mathematical specialty, the fractals. To start, consider the example of the Koch snowflake. In the case of this mathematical curve, the iteration consists to multiply each straight portion by 4/3. Thus, the length of the perimeter develops a dimension greater than 1 without reaching the size of a surface. For this figure of Koch, calculation of its size gives the value of log 4 divided by log 3, or 1.26. And because the size is a fraction, this curve is a fractal. And, with the help of powerful computers, this mathematical specialty helps provide outstanding figures. But, in parallel, we discover that nature also produces fractal morphologies with the reproduction of the same pattern at each scale level. And now we discover that our universe also has a fractal structure, especially with the distribution of stars and galaxies together. And more particularly still, the structure is that of a sponge, or a fractal foam. And this is very important, because following the rule of fractals, where the morphology is preserved at any scale, we must consider logically at the level of subatomic particles, that chaotic torus underwent structuring of the foam at the end of the expansive era. In this way, look what happens to torus operating in a fractal morphology of foam. To complete our approach of subatomic particles, let's present now our third tool, respecting the laws of structuring bubbles and foams. First of all, at the beginning of the inflammatory era in the original substance called primordial soup, some kinds of empty holes appear. Then gradually, at the scale of millions of years, these holes of void begin to expand, forming the engine of inflation. As for beer, bubbles join together to form foam, with bubbles of various sizes. So, the first rule that can be used is that bubbles passing from isolated spheres to aggregate foam, the walls flatten and become increasingly thin. At the subatomic level, the torus will be completely crushed and will become different shapes cycloids. Therefore, in this last inflationary step, these elements pass from the volumetric 3 dimension to dimension 2 as flat surface. But these bubbles' walls are transformed into so thin borders that they become fragile and will burst. And in this case, the first burst of a bubble causes those of neighboring bubbles. And this brings us to another feature of the foams, the notion of breaking point. Indeed, like avalanches, one gathers under the term percolation, these slow evolutions of a process that ends abruptly by a breaking point. Thus, at the end of the inflationary era, all the bubble walls will then burst suddenly in a very short period compared to the long duration of the universe. And it is during this very short time that the space was filled with a majority of limit circles, but also a multitude of flat cycloids. This allows us to say that the basic matter consists of many strings describing cycloid curves, and the notion of mass is then proportional to connect to the inertia of surface insulated by each loop cycloid. But a problem arises because the life of most elementary particles is very short, less than 15 minutes for the neutron and less than a second for mesons. So the question is very simple: why proton life is so long, more than billions of years? To give an answer, we will use the fourth tool, the rules of quasicrystals.